This is Matt Dean with A Plus College Ready, and today we're going to talk about forces. Before we do, let's talk about a couple of branches of a field of physics known as mechanics. One of those branches is called kinematics. Kinematics is concerned with the motion of objects, but it does not take into account the forces that cause that motion. Dynamics, on the other hand, is the branch of mechanics concerned not only with the motion, but how forces and torques cause and change that motion. A force simply can be defined as a push or a pull that changes or tends to change the state of rest or uniform motion of an object. It can also change the direction or shape of that object. The units that we use for force, at least in the metric system or SI system, are newtons, and in the English system, pounds. We'll come back to that in a second. We're going to talk about 4 fundamental types of forces in this class. One of them is the gravitational force. And this is the force that acts between all objects with mass. Compared to the other types of forces, it's pretty weak, but it can act over vast distances. For example, the sun is pulling on Earth, even though we're somewhere around 93 million miles away from the sun. All objects with mass have a gravitational field or gravitational force. Second one we're going to talk about is the electromagnetic force. This is the force which exists between all particles which have a charge, an electrical charge. It tends to be stronger than the gravitational force. It can act over long distances, maybe not quite as long as gravitational force, but it can act over very long distances. Next, we'll talk about the strong nuclear force. This is the force that essentially holds together the nuclei of atoms. It is very, very, very strong, but it only acts over tiny, tiny distances. And then finally, we'll talk about the weak nuclear force. This is the force responsible for nuclear beta decay and some other types of decay processes in the fundamental particles. Like the strong nuclear force, its range is very, very small, and it's not as strong as the strong nuclear force, as the name would imply. So next we'll mention Newton's laws of motion. And the first one of those is Newton's first law. It's sometimes called the law of inertia. It essentially says that an object at rest will remain at rest unless acted on by an outside or external net force. It also might say that an object in motion will remain in motion unless acted on by a net external force. Mass is another way of measuring an object's inertia. Objects with more mass have more inertia. Next, we'll talk about Newton's second law. Newton's second law is best summarized in a formula, which is F net equals ma. Net forces are equal to mass times acceleration. On the AP Physics formula sheet, you'll see it written as sigma F equals ma. This formula gives us a good way to look at the units for force. So we're saying that force is equal to mass times acceleration. Mass we measure typically in kilograms. Acceleration we tend to measure in meters per second squared. So one of these is equal to 1 Newton. The idea of net force is huge. So let's say that you had a box and something was pulling on the box this way to the right with a force of 10 newtons. Something else is pulling on it this way with a force of 5 newtons. Something else is pulling on it this way, force of let's say 2 newtons. Something else is pulling on it this way with a force of 2 newtons. Well, notice we have 2 newtons up and 2 newtons down. Those cancel out. We have 10 newtons to the right and 5 newtons to the left. Well, this 5 cancels out 5 of these. And what we're left with is 5 newtons to the right. That's what we call the net force. After all the forces are added together, some of them have canceled, the net force is what's still left, what's not counteracted or canceled out by another force. Newton's second law is one of the most important ideas in physics. We'll use it almost every day in this course. Lastly, we'll talk about Newton's third law. Newton's third law is sometimes called the action-reaction law. It states for every action, there is an equal and opposite reaction. So when you push on the floor pushes back on you. When Earth pulls down on a falling ball, the falling ball pulls back up on the Earth. That's Newton's third law. Something else we need to talk about is the difference between weight and mass. Mass is essentially a measure of the amount of matter or stuff, atoms and such, that an object is made out of. It doesn't matter if you're on Earth or the Moon or Jupiter, you still have the same mass. You're still made out of the same stuff. Weight, on the other hand, is a measure of the pull of gravity on an object's mass. Weight varies depending on where you're at, your location. The most basic way to calculate weight equals mg, which if you think about it is just another way of writing this. Force equals ma. Weight is a type of force. M is mass. And g here is the acceleration due to gravity, or on Earth, 9.81 meters per second square. We know that g, that value, will change though based on where you're located. We're also going to talk about what are called contact and non-contact forces. A contact force, as its name implies, is a force that's applied by objects that are actually touching each other. They're in physical contact. In this class, we'll deal with several kinds of contact forces. One of them is the frictional force. We know friction is a force exerted by a surface, and it acts in the opposite direction of the motion of the body across that surface. The normal force is one you may not have heard of before. The normal force is a support force. It's exerted on an object that's in contact with another fixed or stable object. It acts in a direction perpendicular to the surface upon which the object is resting. For example, if a box sits on the floor and the box weighs 20 newtons, well, that 20 newtons is pushing down on the ground. Well, according to Newton's third law, the ground has to push back up with an equal but opposite force of 20 newtons. So when an object is on a flat surface, the normal force is equal but opposite to the weight or the force of gravity. Now, when we get on inclines, that will change. We'll deal with that later. Applied forces are also contact forces. So applied forces might be a force we apply with a rope, or it might be that you push a box. When you literally apply a force to an object, that's an applied force. Non-contact forces are when a force is applied on a body by an object without direct interaction or contact. These are oftentimes field forces, like gravity that can act over distance, also the electromagnetic force. And inside the nucleus, we have non-contact forces like the strong nuclear and the weak nuclear forces. Now let's talk about friction for a second. We're going to talk about three different kinds of friction. First of all, we have static friction. Static means not moving. So it's a force that keeps an object at rest. To get an object to move, you have to push on it or pull on it with enough force to overcome static friction. Kinetic friction, on the other hand, kinetic means moving. Kinetic friction is the force of friction that acts between two surfaces that are moving, and it acts in the direction opposite of the motion. So it resists the motion. Rolling friction is very similar, except this is the force of friction that happens when something's rolling on wheels or something like that, or a ball is rolling, a tire is rolling. Typically, static friction, and I'm going to use S for static, that frictional force is going to be greater than the kinetic frictional force, which is going to be greater than the rolling frictional force. Now this is assuming we're talking about the same two surfaces rubbing against each other. In terms of causes of friction, friction can be caused by the roughness of surfaces. Even though smooth surfaces may look and feel smooth, on a microscopic level they're still not smooth. They're still rough. Also, you get some frictional force because of the electromagnetic interactions between surfaces and atoms. When we're dealing with friction in this class, we're going to use this equation to calculate it. I oftentimes call this the fun equation. So it's the frictional force, FF, equals, this is the Greek letter mu, times N. Mu here stands for something called the coefficient of friction, which we can think of if we rearrange our equation as the ratio of the frictional force to the normal force. N is the normal force. Remember that friction always acts in the direction opposite of the applied force. And something that we haven't mentioned, the amount of friction is almost independent of the amount of surface area between the surfaces in question. It's independent of surface area. Remember that net forces cause motion or changes in motion. Whenever there's a net force, there's going to be an acceleration. Remember Newton's second law. F net equals ma, or summation of F equals ma. We're going to see that law over and over again in Physics 1. Something else that we're going to see a lot in this course are free body diagrams. Free body diagrams are diagrams used to show the magnitude and the direction of all the forces acting on an object in a given situation. Key point, when you're drawing free body diagrams, you do not include the components of forces on the diagram. You only include the real forces, no components. So let's look at some examples of a free body diagram. Let's say a box sits on a flat horizontal surface. And my drawing is pretty bad, but I think I can handle a box and a surface. It's pulled with a horizontal force to the right and it accelerates. A frictional force also acts on the object. Draw a free body diagram for the box. All right, well, let's think about it. Let's think about vertical and horizontal forces. The box isn't moving vertically, it's not accelerating vertically, but there are some forces that act vertically. Typically, we're going to draw those forces from the center of mass. One of the forces that acts on it is the weight. That acts down. Weight always acts down. Since this thing isn't moving or accelerating vertically, we know there also is going to be a support force, a normal force, and it's going to be equal but opposite to the magnitude of the weight. So we draw another arrow straight up, and that's not really straight. It should be the same length as the weight arrow, and we're going to label that Fn, in this case for normal force. We also know we're applying a force to this object, and we're applying it to the right. I'm going to name that Fa. It's my applied force. And there's also a frictional force. Now remember that friction always acts in the direction opposite of motion. We know in this case that there is a net force because this box is accelerating. It's accelerating horizontally. This force and this force, the weight and the normal force, they cancel out. There's no net force vertically. This should tell us that the applied force is larger than the frictional force. So we're going to draw in the frictional force, but we're going to draw it with an arrow shorter than our applied force arrow, and we're going to label it like so. So this is our free body diagram, in this case, a diagram that shows all the forces acting on the object. Longer arrows mean bigger force. Here's another situation. Here we have what's called an Atwood machine. Common setup in a physics problem. And we want to draw a free body diagram for both boxes. So we have a box M1 up here, connected via a rope and a pulley to box M2, which we're assuming is falling. So for M1, so this is M1. M1 sitting on the table. It's got some weight. It's sitting on the table. It's not accelerating vertically, which means there's also a normal force that's equal but opposite to the weight. And in this case, there is a force pulling it to the right. And that force is coming from a rope. We tend to call those kinds of forces tension forces. Let's assume for right now, it doesn't tell us in this problem, but let's assume that there's no friction between the table and the box. If there is no friction, this would be our complete free body diagram for box M1. Now for box M2, we don't have any horizontal forces acting. We only have vertical forces. We have the weight of the box, and we also have a force in the rope that's acting to pull this box up, a tension force. And we know this box is going to fall, and it's going to accelerate as it falls. That should tell us that the weight force is greater than the tension force, so we'll draw that shorter than that weight arrow. This is our free body diagram for box M2. And that's it for forces. Hope that helps.